So our next speaker is Professor Fedrizzi from Queensland, and his title is Measurement on the Reality of the Wave Function. Could you please start?
Thanks, Julian. Yeah, hello, can you hear me? Yeah, all good. I'll also thank the organizers obviously for inviting me and giving me the chance to talk here. And in particular for scheduling my talk on the Sunday, because everyone knows that the most interesting speakers are always scheduled on the last day, because otherwise everyone else would disappear before that, right? Measurements on the reality of the wave function, that's the main topic, but I'm also going to talk about some other work. So the last few years I've spent at this beautiful place in Brisbane. That's the University of Queensland there in St. Lucia, and it's snuggled on this peninsula surrounded by the river. It's a really beautiful place. I recommend you visit if you can. Sometimes it doesn't look so great.
I was going to say.
This is in the 2011 floods. Luckily physics is on a hill, so it was high and dry, but everything else was underwater, and you can see how the water here is deeply into the city, so it was pretty bad. I don't have to worry about these floods anymore. I'm now going to move to a place which always looks like that, brown and muddy. That's Scotland. So I'm taking up a new position in Edinburgh, and so that's around here at Heriot-Watt University. And Edinburgh really is a very nice city. So if you're ever around up that way, just come by and visit once I'm there. So this is the university itself, named after James Watt. I don't know who Heriot was, I think he was some economist. And it's going to be experimental positions available later this year. So if any of you students may be interested, come talk to me. The work that we've been doing in Brisbane, that I will be doing in Edinburgh, and that I'm most interested in, is essentially split up over 4 areas. And you've seen some of that already from Andrew White's talk. It's just that my priorities are a little bit different than his priorities. So I'm very interested in photonic engineering, and that's essentially making all the tools that we need to create quantum light, to manipulate it, and to detect it. And so one example that I picked from earlier this year from this particular thing that we're doing is this heralded integrated gate that we made with the guys at Macquarie. So Mike Steele was part of that. And so what this is essentially a 3-dimensional quantum gate with direct right waveguides, which is supposed to be a heralded C0 gate. So we essentially made those 4 modes in the middle that do the heralded phase shift. So if you really want to do linear optics into the future, we need to move to these heralded gates. Because we know that the 1/3 beam splitter that we've now seen many times, that obviously doesn't scale, so that just limits us to a depth of a single gate. So I don't know what that means for 2D architectures. We've seen very nice examples of reconfigurable chips, but the problem with those is that the gates that you can make with those, the 2-photon gates, aren't really heralded, right? So they are still just a 1/3 beam splitter, and that doesn't scale. So that's something that definitely needs to be addressed and I think it's going to be very hard in these planar architectures if you can't introduce any nonlinearities. So essentially what the issue is with the heralding, and so this is just a gate by Neil, but there are others. So the issue is that you have frequent crossovers of these 4 involved modes, where 2 are the ancillas and 2 are just the involved qubit states. And so you need to swap modes around quite frequently, and in the 2D architecture is really hard. So what you really need to do is you'd need another 3 C0 gates just to make a swap, and of course those C0 gates would also all have to be heralded, and so you just can't get out of this problem of sort of making heralded gates in these 2D architectures. So have a look at that paper if you want. So the second area that I'm interested in is obviously applying these tools to quantum computation and communication. The example that I picked that was published earlier this year is in tomography. So tomography is one of the big bottlenecks in quantum engineering in general, because we know that the bigger we make our devices, the harder it is to actually characterize them. So we've heard many things already about efficient characterization and about validation and all these things. So this is a real problem that people are working on right now, because it really limits us to very small devices. We cannot do tomography of big devices. So what we did here is we showed that normally processed tomography of a single qubit system can return some result which sort of already accounts for possible correlations with some environment. But what it doesn't account for is if there is really some initial correlations that can get affected by preparation procedures. So what you have here is you have a system that we're interested in, and presumably we're trying to do a single qubit unitary on that, and we're trying to do a process tomography of that. However, if our system has some correlations with the environment, then the specific preparation procedure that we choose here to sort of initialize our quantum states, that obviously will leave the correlated environment in a state that depends on your essentially initial projection. So what we do here is we demonstrate how you can take that preparation procedure into account in a superchannel approach. And so without going into detail, we have to look at the reference. So the superchannel approach essentially shows you the effect of these initial correlations very beautifully. So the third example is from quantum simulation and emulation. And this is something that you already heard earlier from Matthew Broom. So what we did here is we looked at the effect of decoherence on quantum transport and showed in a very simple waveguide system, again direct right, but this time with Alex Samad and not with the guys at Macquarie, that decoherence can essentially enhance quantum transport through a system of waveguides. So yeah, I have got the correct reference here, obviously. So, but the area that's closest to my heart, and that's going to be the main topic of this talk, is quantum foundations. And what I like to say about quantum foundations is that, sometimes we forget that, so most of us are interested in building big quantum devices and quantum computers and all that kind of thing. But sometimes I think we forget what we're actually trying to do with these things, because one would hope that we're interested in building quantum computers because we want to answer some interesting physics. And I feel that very often we sort of slide into mere engineering, forgetting about the fact that we're actually interested in the physics, right? So we're not building quantum computers to factor numbers, we want to answer interesting questions. So my take on this is that if you can answer interesting questions already with the tools we have, then you should sort of stop your engineering and try to answer that question, and then go back to the engineering, because otherwise we sort of, the whole thing is kind of upside down. So anyway, and with that, I'm going to go to the actual talk, which is on measurements on the reality of the wave function. So what is this all about? It's about the following. So just in a nutshell, if you think that there is an objective reality underlying microscopic systems and therefore also macroscopic systems. So if you believe that reality is objective, independent of you observing it, then there's two things that the quantum wave function can represent. So either it represents limited knowledge of this underlying reality, or it corresponds directly to this reality. So here you see the wave function is a real object, over here it isn't. And so what this work is all about is to decide between these two things. And so very generally, there's essentially three broader views you can take of this issue. So the first one is that you could just say, well, I don't care about objective reality, there is no objective reality. So that's a valid view. And the other one is that there is an objective reality. Okay, so those are obviously, that's a big difference, so either you think that or not. And then you can, in regards to the wave function, you can either think that it's epistemic, which means that it sort of just encodes some limited information about some reality or no reality, or you can think that it's ontic, which means that the wave function is really in direct correspondence to this reality. And so, I suppose you cannot really see that, but so this field must stay empty, because obviously if you don't think that there is an objective reality, then it wouldn't make sense to think about an ontic wave function. So just in terms of where the interpretations are, So interpretations which don't think that there is an underlying reality, at least not an objective one, is for example Copenhagen cubism. And then down here we have people like Einstein. So this is a classical, this is what Einstein believed. He thought that there was an objective reality, which is the hidden variable essentially. And he thought that the wave function essentially described our limited knowledge of this hidden variable. And then over here in the ψ-ontic box, you have things like many worlds and Bohmian mechanics and so on. So what we are trying to do experimentally is sort of we're trying to decide between these two things. Can I have a show of hands? Who's in which camp? So who thinks that there is no objective reality? So who is up here? Hands up. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. Who thinks that there are hidden variables? No one? Okay, so we've got 8 here, no one down here. That's interesting.
Didn't check the third.
You didn't check the third one.
Well, I just asked who thinks that there is
Oh,
reality
right,
at all,
well.
and so there was no one. Ah, okay. So who thinks that there is reality at all? Okay. And who thinks that the wave function is epistemic over this reality? No, these guys. So you all think we're done here. Oh, excellent. All right. So one thing that we frequently, one thing that people very often say when they see this at first, this matrix, they say, "Hang on, why are you talking about hidden variables? We already know that Bell rules out hidden variables." Well, that's not quite the case, and so I'm taking my first break, this interlude, and I want to talk about a little bit about Bell's theorem and what is really ruled out in Bell's theorem and what people have been doing experimentally. Okay. So obviously here we have an entangled system, and you all know the story. When this was first discovered in the quantum formalism, then Einstein, Podolsky, and Rosen wrote this seminal paper where they said, "Oh, we think quantum mechanics is incomplete because we don't think that there should be this spooky action at distance where you measure, if you measure one particle, then some other particles' measurement outcomes will correspond to the first one, no matter how far apart it is." So what they said is, they said, "No, you know, the world should really be local." And they said that measurements should have predefined outcomes, essentially. John Bell, of course, formalized it in his inequality. And so in our experiments, what that looks like now is we have a source which spits out entangled particles, and we have two measurements A and B, so two measurement settings on the left and on the right. And then we have two outcomes, capital A and capital B. And if you think about that for a little bit, then you realize that there's some joint probability distribution, which should be a function of some hidden variable, which is essentially the thing that Einstein said must be hidden somewhere. Okay, so that is essentially the objective. That lambda is the objective reality, as we will see later. So there is a number of explicit assumptions here, which is first of all that there are hidden variables, and they can be either stochastic or deterministic, which means that either they just define some probability distribution of some outcome, or they do in fact decide every single outcome. The second one is locality, which essentially means that whatever happens here shouldn't be influenced by whatever happens over there. So that looks mathematically, means that just this joint probability distribution factorizes, and whatever the outcome at A is really just dependent on the hidden variable and the measurement setting here. And finally, the third one, and that had long been ignored, is the freedom of choice or measurement independence assumption, which essentially is formalized like this, which means that whatever goes on should be independent of the setting choice themselves. What this really means, some people interpret this as free will, so they said, so if I choose to do a measurement, then I should really be free to choose that, and it's not like already predetermined since the dawn of time. Alright, so with that you get the CHSH inequality and so on and so on. You all know how that works. Now, the experimental requirements are these ones, so locality, freedom of choice, and detection. So I would like to stress that if you haven't got the first two, you've got nothing, because if you can't guarantee that your experiment, doesn't allow for any local influences, then what can you possibly say about non-locality? Okay? And the third one is a bit of a technical thing, so you need to be able to detect a reasonable amount of the photons or entangled systems that you created in the first place, otherwise you cannot say much about Bell's inequality either. So there are some common misconceptions, and this really drives me crazy. I don't know why you find things like that in the literature. So I don't know who this poor person is. I made them the scapegoat representative of all these people who keep claiming that Bell's inequality has been violated. So for example, nowadays it's commonly admitted that the experimental violation of Bell's inequality that was successfully demonstrated in the last decades by many experimentalists and so on and so on. So that's simply not true, right? Because you have a number of assumptions, and if you don't meet these assumptions in your experiment, then you cannot really make any claims about the results. And so the other misconception that I find very interesting is that so many people just say, oh, clearly Bell implies that quantum mechanics of the world must be non-local. And many other people claim, oh, clearly Bell means that there is randomness. Clearly Bell means that nature is indeterministic and all these things. Well, it turns out that Bell really, the Bell theorem doesn't imply any of these. And so, if you want to know more about that and how these misconceptions come into place and why people are having very strong arguments about it in the science, I recommend to look at this paper by Eric Cavalcanti and Howard Weissman, where they sort of really plow through the history and the literature and sort of write down a new classification for what Bell's theorem really rules out and what assumptions it requires. And so they have these 4 axioms over here and 4 postulates, and they show that these 8 things together is really that's what essentially quantum mechanics refutes. Anyway, so when I looked at the free space lab done at the lab tour, I sort of had these good memories of my free space days in Vienna, so we did these experiments between these Canary Islands, and so you see a telescope here, and in the distance there, that would have been me sitting on some mountain there in the Atlantic, and then sort of sending entangled photons across. And so one of the key experiments I think that we did in this field of Bell inequalities is that we did an experiment which really met the at least both of these locality assumptions. And for me, this is sort of the most complete Bell experiment, because the detection, you can very reasonably argue that that fair sampling really requires a lot of conspiracy. Whereas if you can at least meet these two, then at least you meet the explicit things that go into Bell's theorem. And so, of course, the group of Chan Wei has also done a very nice experiment on this that was, I think, published in the Journal of Physics. I just couldn't find the reference. So the final thing we need to do is to close this detection loophole, and the advances in photonics have really also made a big contribution to the foundations in this regard, because, of course, we now do have high-quality entanglement sources, and we also do have almost unity efficiency detectors, and this is the one in our lab. And so we did the steering experiment where we really showed that you can have if detection efficiencies for entangled photons that are high enough to sort of at least get into the area of doing Bell's inequality properly, and then for local Bell violations in Paul Quiert's lab and in Vienna, they actually have already done this with this detector. And so that concludes my first interlude. What I wanted to take out of this is that, of course, hidden variables aren't ruled out by Bell's theorem. And so, therefore, it is meaningful to talk about the question, what's going on down here. Okay, now, so in order to say something about that, and in order to sort of construct an experiment which can decide between these two things, you first need to define some formal framework for what's going on. So you need to have some formal framework for this underlying reality that you're discussing. And so the framework that people are using is essentially the Bell framework. So the framework that was sort of developed at first by John Bell, and then people started tacking other things onto it. So you can call it the Bell framework or the ontological framework. So in the ontological framework, first of all, you have a set of ontic states, lambda, and that's like analogous to phase space. And any system that you might have in a lab has some value lambda out of this ontic state space that completely specifies all of its properties. And now, when you prepare a quantum state in lab, what you really do is you sample from a probability distribution that's called mu lambda that depends on psi. So really if you prepare some state in the lab, what you get is there is some ontic state down here, which is in this ontic state space, but really your state is this sample from this classical probability distribution over this ontic state. Now, if you think about what happens if you have two quantum states, psi1 and psi2, and you prepare these two in specifically non-orthogonal quantum states, then one of two things can happen. So either these probability distributions can overlap, so this is the state space, remember, or they can be completely disjoint. So in this case, the quantum state would be completely determined by its ontic state, right? Whereas here, I could have some ontic state here, which sort of could correspond to either this probability distribution or to that probability distribution. And now it isn't uniquely defined. Okay? And so this is exactly what the difference is between ψ-epistemic, which was the box on the left, and ψ-ontic, which was the box on the right. So whenever your classical probability distribution that you're sampling from over this ontic state space, when they overlap, your model is ψ-epistemic, and if they never overlap, then it's ψ-ontic, because now the wave function really corresponds directly to the underlying reality.
So is that just the difference between orthogonal and non-orthogonal states?
No, this is all for non-orthogonal states. For orthogonal states, you could have this also in a ψ-epistemic model.
Could you have for orthogonal states?
If your states were orthogonal, then this wouldn't be a big problem even in ψ-epistemic states. So then you couldn't distinguish between the two. But it will hopefully get clearer later. Hopefully. So the question is, how can you come up with a test that shows you which one of these models is physically possible? And so the first ones who made some real progress in this field after, I mean, this had been debated a long time. So, you know, are ψ-epistemic models reasonable? Are they reasonable? But they are very desirable because they solve many problems that otherwise can't be really explained, like Schrödinger's cat, you know, is it dead or alive? What's this all about? In the ψ-epistemic picture, the cat can just either be dead or alive, and we simply don't know, and we don't care, because all that happens is when we open the box, we update our knowledge, but it was always dead or always alive. So that would be a really nice explanation of Schrödinger's cat in the ψ-epistemic picture, so there's some reality, and we just don't know what it is. In the ψ-ontic picture, we have a much bigger problem, because now, all of a sudden, if the cat is alive and dead in the superposition, and if the wave function really corresponds directly to some underlying reality, then the reality of the cat is really to be alive and dead. Okay, so that's a compelling argument why people would like the ψ-epistemic picture to be true rather than the ψ-ontic picture. But then Terry, who unfortunately isn't here, and Matthew Pusey and Jonathan Barrett came up with this PBR theorem, where they essentially said that all ontic models that reproduce the Born rule must be ψ-ontic. So they essentially said ψ-epistemic models just don't work. Yeah, so those are the statements that they made in this paper, and so that kicked off this big interest again in this question of what the wave function really is. There were a number of other no-go theorems. So PBR was just one of many, really. There was also this work by Kolbeck and Renner, then by Lucy and Hardy, Are Quantum States Real? By Serge Massa's group in Belgium, and even Scott Aronson chimed in on the question, and again Kolbeck and Renner. I think Kolbeck and Renner had at least 4 or 5 papers on this topic, most of which are really the same, but that's what they tend to do. Happy to propose something as well. Yeah. Anyway, so what all these guys said was the ψ-epistemic models, so they all tried to construct no-go theorems which said that ψ-epistemic models don't really explain what's going on with the quantum wave function. But it quickly turned out, and this is also a point that Scott's making in his paper, that all of these no-go theorems rely on assumptions which are beyond this ontological model framework. And so in particular, the problem with Terry's paper is that in a nutshell, I mean it's more complicated than that, but in a nutshell, Terry said, is consider these two independently prepared systems, and then he goes on to make his argument. But at this point you can already say stop, because, you know, what are you talking about? Independently prepared systems, you know? What about non-locality, right? So if there is non-locality, there aren't any independently prepared systems, and that's the end of the entire argument, right? So Joe Emerson wrote this comment where he said, well, you know, this sort of independently, this independent preparation that just doesn't work, and if you have to impose locality on top of that, what really end up with is another Bell's argument. So they said really they said the PBR theorem doesn't add anything beyond Bell's argument. I think they were a little bit too critical. Those don't really work. So we needed a different approach, and this different approach was found essentially in this phenomenon of, in the central feature that we of course also know in quantum mechanics, which is that we cannot distinguish non-orthogonal states with single-shot measurements. So we all know that, you know, if we have a state that's, you know, 0 and then we have one which is 45, then we cannot really tell these apart with a single-shot measurement. Okay? And so people have started to look at whether we, instead of having a no-go theorem against ψ-epistemic models, the idea is now to try to bound ψ-epistemic models by essentially characterizing how much overlap there is, and then relating this to this phenomenon of not being able to distinguish non-orthogonal quantum states. And so the first paper that was written in this space was again by Barrett and then Eric Cavalcanti, Raymond Lal and Owen Maroney, where they said that no ψ-epistemic model can fully explain the indistinguishability of quantum states. Okay? So, and that was what piqued our interest, because that looked like you could do this experimentally. But unfortunately, what they say in this paper is that, so they only found a very tiny effect, so they, essentially what they said is you need a quantum system of dimension at least 3, because for 2 dimensions you can always construct a ψ-epistemic model that's essentially a Koch and Specker model. But if you have more than 3 dimensions, then you should find essentially something which can't be explained by this overlap of probability distributions. But what they also said is you need to be incredibly precise. So you needed less than 10 to the minus 4 something error to do this experiment. Now that sounds very hard, and at this point I'm going to take my second interlude to show you that 10 to the minus 4 shouldn't be scary for you if you're working with photonics. And that's another big advantage of photonics, that it can be very precise. Okay. So I'm going to take you back 2 years to a paper on joint measurement uncertainty, where precision really mattered. So this again was on something which is very foundational, which is Heisenberg's uncertainty principle, and you of course have all seen this here, where the error in x and the error of p, if you multiply them, they must be larger than h power 2. And so this is what we commonly know as Heisenberg's uncertainty principle. But if you dig a little bit deeper, then you will find that actually Heisenberg's uncertainty principle makes at least 3 statements about nature. And so the first one of these is that if you have 2 incompatible observables, then these cannot be arbitrarily well defined on a quantum state rho. So that's essentially preparation uncertainty when you prepare a quantum state. And so you have to be very careful of how you characterize these deviations, and that's where a lot of the confusion that later emerged came from, because people started defining these things differently. But if you do it properly, like Robertson did here, then for some error in the observable, which here is defined as some trace distance, this is essentially the new uncertainty relation. Now, the second statement that you can make is about joint measurement uncertainty, which is that the observables A and B cannot be jointly measured on rho with arbitrary accuracy. So if you have some system and you're trying to do a joint measurement of A and B, then you cannot reach arbitrary accuracy. Now you need, and again you need something how to quantify this accuracy, and so essentially what you end up with is with the question, what's the optimal trade-off between some inaccuracy on the observable A and some inaccuracy on the observable B. And now finally the third one, which is a little bit, so it's actually related to the second one, and we treat them almost the same in our work, is that a measurement of A, if you do it sequentially, if you measure some observable A, then that will disturb some subsequent measurement B. And again, you need to think of how are you going to define that, and so again, people have come up with some definitions. So the whole brouhaha essentially here was that Ozawa, more than 10 years ago, came up with the so-called violation of Heisenberg's uncertainty principle, right? So he said, well, it turns out I figured out this measurement disturbance relation, and I find something which goes below what Heisenberg claims we should have. So he said, oh, look, Heisenberg's uncertainty principle is violated, you know? And of course, because we were really greedy in photonics, you know, people started doing experiments, and then, you know, the headlines came out, Heisenberg violated and all of that. And that very justifiably drew loud criticism from people like Reinhard Werner, who said, well, hang on, you're not doing this properly. So if you want to see a really nasty literature discussion on the archive, I recommend looking in into these papers by Ozawa, and on the other side, Werner and Paul Busch. And so there are comments and comments to comments and criticisms on comments to comments. It's very nasty, people calling each other names in scientific publications. So essentially what the disagreement is about is that Reinhard Werner is claiming you're not doing this properly because your uncertainty relations, which presumably violate Heisenberg, are state dependent, and they shouldn't. So it turns out if you look at specific quantum states, you can always go a little bit lower than Heisenberg, but if you define these things on different quantum states and sort of work out some average disturbance, then you essentially just recover the Heisenberg bound. So we weren't so much interested in this discussion. What we were interested in is to at least do the state-dependent version properly. And so what we ended up doing is Cyril Brandt, a colleague at UQ, found some tight relations because what Ozawa had written down wasn't tight, so it couldn't be saturated. And Cyril Brandt wrote down tight relations, and that's what we did experimentally. So there's just quickly, there's two things you can do if you want to quantify these inaccuracies of joint measurements. So the first method is the three-state method. That was the one that Ozawa invented. And so essentially what you do is you send three states into your measurement, you measure A and B, and then you figure out what the disturbance is, what the joint measurement inaccuracy is. And in the experiment, that's in fact very simple. You just do a single photon experiment with a heralded photon. And what was the important thing for us is we really wanted to get as close as possible to these tight relations. And now the number that I want to point out to you, the numbers I want to point out to you are down here. So the average purity in this particular experiment was 99.917, and the average state fidelity was 99.917 again. Is it the same number? There must be something wrong. So it's one of these is wrong. Now, the other method that you can do in order to figure out these joint measurement uncertainties was in fact developed by Austin in 2010. So essentially they devised this weak state method where one of these observables is implemented as a sort of a weak measurement of either A or B, and then you estimate these disturbances from the probability distribution of the measurement that follows this weak measurement. This experiment was a little bit more complicated, so now you need a CNOT gate, which of course we can also do in optics. And now the numbers look even better. So if you just looked at the state fidelity of the reconditioned state here, the state fidelity was 99.998. And so this is something where we really try to get to the limits of precision. And these are quite really good numbers if you consider that these are achieved with just the standard wave plates that you buy off the shelf. So I know that other architectures, of course, are also have also really good numbers there, but in optics it's essentially just a cheap wave plate that you buy of some catalog. All right, so if you if you do the analysis properly, and that was the other problem that we had with previous existing literature, they said no one had done this properly because people just applied the ideal measurement, the ideal three-state method and the ideal weak measurement method, and then started to just chuck the error bars on top. and that was all wrong. What you really have to do is you sort of have to adapt these the three-state method and the measurement method to states that aren't pure. Because if the states that you send into the three-state method aren't pure from the start, then you cannot just use the ideal protocol. Anyway, so as you can see, we get really close to these tight relations. So here's for the measurement and disturbance, and here's for the joint measurement uncertainty. So that concludes the final interlude, and what I think you what I hope you took away from that is that photonic quantum information processing is very accurate and precise, and that's a very good thing for foundational research, because sometimes you do need that. And so in particular we needed it for this experiment. Luckily, so the protocol worked out by Eric would still have been very hard, but luckily Matt Leifer and again Cyril Branciard at UQ did 2 follow-up papers where they showed where they sort of relaxed the really hard conditions in this original paper and made them a sort of a little bit more experimentally friendly. Okay. Now, what's this? Right. Okay. So how do you distinguish between the ψ-epistemic and the ψ-ontic model now? Well, you need to classify, you need to characterize or quantify these overlaps of these probability distributions. And so what we have is, we of course know what the overlap of 2 quantum states is. We can just simply calculate that. We usually take the trace distance. And so here's a measure, it's called omega q, and that just measures how far apart our 2 non-orthogonal quantum states are. And then here for the classical states, so these are the classical overlaps, you come up with this, again with some classical trace distance between classical distributions, and this ends up being something that you can measure in some experiment. And now, if your ontological model wants to reproduce quantum statistics, then the classical overlap strictly needs to be smaller than the quantum overlap. Specifically, if the model is maximally ψ-epistemic, which means that all of the overlap is explained by these classical probability distributions over ontic states, then these 2 things, the classical overlap and the quantum overlap, must be the same. And what you're essentially trying to do in your experiment is you're trying to show that, of course, we like inequalities, and so we rewrote this as an inequality, and we also called it S because we were really creative. So what you're trying to do is you're trying to get this value, which is a ratio of the classical overlaps to the quantum overlaps, you're trying to get this experimentally below 1, and if you get it below 1, then you have violated maximally ψ-epistemic models. Now the protocol is you prepare a set of n+1 quantum states with at least 3 dimensions, so you need Q-trits or Q-quarts or Q-quints and so on. And for each triplet of these states, you again perform measurements with 3 outcomes, and then you have this really nasty looking upper bound for the classical probabilities, and the measure for the quantum overlap, and in the end you want to get this number below 1. So this is what the experiment looked like. It's a really simple experiment, but again it had to be extremely precise. So you have a photon that goes into this beam displacer interferometer, and so here we just have half-wave plates. We should set up a Q-quad state in this part, and then here you essentially have a measurement where again you sort of recombine these things. And so what this is a Q-quad in polarization and mode, so that's 0, 1 in this mode and 2 and 3 in this mode. So very simple, but still very demanding because you need to get very high precision. We did a lot of characterization of this precision. I'm not going to go into detail here. You can look it up in the paper if you're interested. So here are the results. So for Q-quarts, what the theory predicts, so the theory predicts that if you go, the higher the dimension is that you have, the faster you can get this ratio between classical and quantum overlaps to 0. And so for Q-quarts, this is what it roughly looks like. So this really cannot be calculated analytically. This is essentially just a dodgy, almost brute force search over the state space. So down here you have the number of states that are being prepared. And so the more and more states you prepare, so essentially if you could prepare 1,000 different Q-trit states and then could do 1,000 squared, like 1,000,000 measurements of this, then essentially you would be able to bound these overlaps to almost 0. Of course we cannot do that because it would take too long, and we also run into the problem with the precision. So this is the theory curve, So for 15 states, you would hit 0.6 for this value of S, which characterizes the ratio of overlaps. And so if we put in our experimental parameters, which is essentially the error per measurement, then you can quickly see that you cannot actually make any progress for Q quads below the value of 0.7. So this is our achieved accuracy. So even with 4 9s or 5 9s, you turn around here. So the data points are pretty close to that. And so what we achieved in the experiment was a number of 0.69 with many standard deviations. So again, precision is a problem here. So we estimate that the fidelity of our projective Q-tip measurements is above 0.9993, and yet it's not good enough to get under the value of 0.69. You can also do that for Q-trits. I'm not going to bore you with that because it's getting late. Important here only is that so what essentially we only did 3 Q-trit states because it was quickly clear that that wasn't the optimal thing to do for us. But what you saw there was that at least the theory was confirmed that from Q-trits to Q quads, it's much better to sort of go to the higher dimension. It drops off to 0 far more quickly. So ideally, you'd like to do that in a very high-dimensional system. You'd like to do this with the OEM modes in 100 dimensions or something like that. But I really doubt that you could do measurements on OEM which are precise enough in that kind of dimension in order to make any improvement on these results. It's a little bit similar with chips. So ideally, you could say, for example, have Alberto's chip or Dirk's chip here and do this with in 10 dimensions or in 20 dimensions. But again, you'd have to beat the precision. All right. So where does it leave us on this chart here? Well, presumably, what this does is it rules out some people's favorite box here, which is the one that Einstein believed in. So what we're now left with is either that there isn't any objective reality, or that if you think that there is objective reality, you need to seriously consider the ψ-ontic models, which contain many worlds in Bohmian mechanics. So it's now the time to sort of choose a new box if previously we were in this box. Of course, that's not the whole story, so people still hope that this could be salvageable, and they say that, if you, for example, if you chucked retrocausality into the mixture, so if you, for example, move beyond this ontological model framework, then you could maybe salvage something here. So I'm sure we're going to see more in that space. We also got an email from Robert Griffiths, who propagates consistent histories, and he also wasn't too happy with our conclusions. But I think we've resolved the difference now. So the question is, where do you go from here experimentally? Well, obviously you want to go down here, because the problem is that our results really just rule out maximally ψ-epistemic models. So that means that not all the overlap is explained, but some of the overlap some of this non-distinguishability of non-orthogonal quantum states could still be explained by essentially epistemic models. They just cannot be maximally ψ-epistemic. So you really want to push this down to as close as 0 as you can, and we're currently working on that. All right, and that's it. Thanks.
Thank you very much. So, do you have any questions? Okay, please.
Carlo, do you think that there's potential for applications? I'm thinking about an old paper by Jeff Wright in which they have used contextuality for some cryptographic tasks. Do you think that these things can be used for something?
I think I reject the question. I think the application is to learn something about the wavefunction. No, I see what you're saying. I really don't know. I don't know. Okay.
So, any other questions? Actually, I have one question about your last part of your talk. I'm wondering, how about the detection loop for your case?
Yes.
I mean, you may need some fair sampling assumption even in your case, right?
Yeah.
I'm not sure.
Yeah. No, it's true that there is a detection loophole. So also here you'd have to take into account in these inequalities the fact that you can detect all photons. And if you try to figure out what the detection threshold is to get a proper violation, then it's prohibitive. So it's far harder than the Bell inequality. I think it's in the protocol that we worked out. I think it was going to be above 98% that you need to for the detection probability. And so yeah, we make the fair sampling assumption here as well.
I see, but I'm a bit interested in the different. Sorry, maybe I should. So please.
I think it's really very brave that you have given this wonderful talk, because I think it's completely different from most of the other talks. And the audience consists of computer scientists and people who want these applications. And I think, yeah, I would like to copy that speech of yours sometimes, or why it is important to do foundations. So, but then this is a non-academic question. So, how do you actually pitch for funding?
Funding?
Funding, yeah.
Who funds this crap, as she said?
Well, I think luckily that there are people who fund foundational research, and there's actually quite some money in it if you yeah.
FQXI
exactly,
and Templeton will fund this.
Exactly. So in fact, we have a project funded by Templeton, but that's on a different topic. That's on causality, which of course is one of the hottest topics in foundations right now. And so they fund us with a very large interdisciplinary project between philosophy and physics. So we end up having these joint seminars, which is very interesting. And there's a workshop on that in Brisbane in August that is run by Jared Milburn and his philosopher friend Phil Dow. So if anyone wants to come to that.
So do you always have to be unconventional?
Mm-hmm.
So do you always have to prove that you are unconventional? Or, you know.
No, you don't have to. You don't have to be fancy outside the box contrarian to claim that quantum mechanics is broken. I think they really just want to see some progress on the big questions. That's what they call it, and they're also interested in sort of doing interdisciplinary things. And so philosophy and physics is a good mix in that regard. But the FQXI funds smaller projects, and I think that people have more.
They even funded me, and I wasn't crazy.
Okay.
But I don't believe in reality.
So how do we distinguish between reality and unreality?
Yeah.
Yeah, that would be a very interesting question, right? So how do we? So when Andrew talked about this in Brazil last year, Adam Capello afterwards told him, I know how to distinguish between reality and no reality, but I'm still working it out, So I have to catch up with him to ask him about that at some point.
But that's the whole point. The fight is down here in the two lower boxes. If you are in this upper box here, there's no fight.
Yeah.
That's true.
Well, we want to create the fight and then publish.
Well, he wants to create a fight between the upper box and the lower box.
And then publish something.
Yeah, I think many people just say, why should I care about this? I think Copenhagen is, shut up and calculate, and why do we care about this? But I think there's a very compelling, but they have other problems that they can't answer, right? So explain Schrödinger cat properly in that picture, and all of a sudden they start So I think that many people who say that they don't believe that there is objective reality, if you really question them, ask them some hard questions, that they would eventually discover that maybe they were sort of crypto-realists all along.
Crypto-reals.
Crypto-realists,
Yeah, China might be a good place for discussion because ancient Chinese philosopher mentioned about the distinguish between reality and non-reality. Anyway, any other questions or comments? Yeah, I have to ask one question later, but okay. If not, let's thank the speaker again.